Alright, today on the bench, a Nixie instrument, the 5327B timer counter DVM from HP, of course. And I saved that from a Hamfest. It was going to be taken apart. So this one's from Varian, apparently, down the road. I'm going to give it a good clean and give him a quick inspection. Look how it is inside. Okay, ooh, okay. So I was told this one had the high stability option, but I don't see it. Yeah, I looked it up and this board is actually the oscillator assembly. And the reason I didn't see the quartz crystal on it is that it looks like a transistor. It's written Bulova on it, 10 megahertz. So that's just a regular oscillator. What I do see though is it has this stuff that matters. It has the extra digit, so it's 8 digits. I also see that it couldn't possibly work because somebody had left solder in it. Solder splash in here. Okay, so we have to scrape that. Let's remove the solder splatter. I really wonder how it made its way there. Okay, no fear. How do you turn the thing on? Not here, not there. Missing something. Fuse looks okay. Nothing! Okay, there's an on-off switch somewhere that I'm missing. That's my problem. Yeah, it's over there. So I tried to wiggle that and that didn't do a thing. Maybe I didn't wait. Yeah, no, it's on. Okay, well, no. That's the same as the older instrument. That this is the on-off. But you know, maybe the there we go. It's an old switch. Life. Well, that is good. All right, so let's give it the beans. Let's see if it counts anything. It has a very faint one over there. No. 0. We are not counting 100 kilohertz. Not counting. Start. We should be able to count. Oh, here we go. We count. See how fast it can go. It's counting at least on 1, 2, 3, 4, 7 digits. There you go. Faster. Yeah, all digits work. Woo! And then let me count to 10 megahertz. Megahertz. Yoo-hoo! But I am not measuring frequency for some reason. So wait a second, I just looked at the back and it's on external oscillator. So that might be my problem. No. Aha! There we go. Okay, normal. What? Frequency A. That's not what it should do. Because it's not resetting. It should count, reset, count, reset, count, reset. But since it's not resetting, it never gets it right. Only the first digit resets. Okay, so let's investigate the reset circuit. And I see the reset signal. That's the one that happens every time it counts. And that's the manual one, so that's all perfect. This digit resets correctly, and that's on this board. and the other digits that don't reset correctly are on this board. So that's my board with the Nixie drivers, and it's very regular except for the first column. There is no reset that goes in it. So this is a high-speed counter driven by the external board, and then there are all the normal TTL counters. That's reset. So let's see if we have something on pin 14 of these circuits. You can see the reset line, that's this one, goes to every pin 14. So let's see if we get something on that line. Yeah, it's not making it. On the top, that's the one that I'm getting from the board that's generating the resets. That's this one. And the green one is this probe. And we have Zippo 0 on it. It's at 0 volts. Okay. So why is that? Because it makes it to the board before, so it seems to be just a contact issue somewhere. So let me see how the reset is handed over from board A8 to board A9. That seems to be our problem. So that's board A8, which is essentially this high-speed ECL decade counter, and the reset comes in here. And for the decade counter, there is a level translator because ECL works with different negative levels, so it goes to -5 volts. So this makes it, but then it goes straight through and should come to the other board. So we should just do a continuity test and figure out where we lose it. It makes it to the board A8. It makes it on. It comes in to CR1. Yep, it's there, and then it should continue straight on to here, and it's not there. Let me take the boards apart. So this one we could take on the bench. It's on this pin here. Can I take the other board out? I probably can. Look at this. These are pretty Nixies. So I reseated it, and now I have it. So it's a problem with the contacts in here. And now I suppose it would work. On the good side of things, since we went and took that off, we get to clean our dirty Nixies. A little bit of deoxide gold. That never fails. Deoxide has always repaired my contacts. It lubricates too, so it makes the connectors much easier to, oh, you can tell. Okay. Alright. I'll put this back on here. Alright, so reset makes it. Okay, let's try it again, see if it made a difference. There we go, now it works. That was just it. And then I can make it count. Start. Stop. If I do a reset, it goes to 0. Huh! Goes to 1, 0. So we have an interesting issue with our digit here. It starts at 1 instead of starting at 0. It's a weird one. Sorry. Dim 1, 1, 2, 3. Oh, 1 is always kind of on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. Okay, so we might have another issue here. Remember, that's the digit where we had the splash of solder, so maybe an IC issue or something of some short circuit remaining in there. So looking at our board and the pinout of our chip, which is a special HP chip, which they had to do because they wanted blanking, and looking at our former footage, the solder blob was exactly over the top of C0, C1 and C2. It was right here, and I wonder if there's still some high resistance material left. I removed the circuit and it appears kind of clean. So I scratched around here. Also at the bottom it was slightly dirty over here. Could go with a meter and verify that they are all nicely isolated. Sometimes it doesn't take very much. Okay, I put the IC back in place the best I could. I cleaned the flux and oh, the issue is still there. It has to do with the blanking, right? So I would say at this point the driver IC is suspect. It's not blanking correctly. Unfortunately those are rare. So we'll see if I can find one. If not, we might live with it. So at this point we'll consider it good enough and I'm going to start to do the adjustments, which always on this type of devices, since they have analog parts, consists of adjusting the power supply. Should be 16.5, that's the minus. Alright, let's do the other supply. And the other supply is a little flat 2, 16.39, going down as it's heating up. Okay, we'll consider it good. And for the next adjustment, the manual calls for using an oscilloscope 180 from HP. And we're happy to oblige. There it is. This is actually my newly acquired 180 and I hope it stays with us because it was a little cantankerous. It was a little cantankerous in brightness. There is a marker output at the back, and also on this scope there is a Z input at the back, which is basically the brightness, and that gives you quite an interesting bit of information. So if there you go. So now when I have put the marker, you see there is a little dot, and that's the dot that tells you where it triggers, and you can trigger on the upslope or on the downslope. There is a switch in the front. There is some hysteresis between the two, and you want it centered about 0. It's not too bad, it's a little low. So it's board A2. This adjustment, yeah, goes up, goes down, and you want to make it about symmetric, about 0. So that's 2. There you go. By the way, you can move it, right? If I go over here and I go here, see, I can choose exactly where I trigger. So I can trigger at exactly 0 if I want. The problem with that, if you put it in the mode trigger A to trigger B, usually if you want to trigger on the up and then on the down, you would have this hysteresis to it. So what they do, they compensate for that in this mode, which is A to B, and as you see when I go on the downslope, it's almost at the same value. And oh, here's my cantankerous oscilloscope moving away from us, and the goal here is to have it stay the same in plus and minus, and there's an adjustment for that. There you go, much better. Now it's the same. And then it says repeat the procedure for channel B, which is over here, and there is marker A and marker B, but I have a problem. B doesn't work at all. So I think my amplifier B is not working. Well, I've just taken the two cards out. That's A, that's B. They're supposed to be the same. There's a little problem with B. B is missing 2 transistors that A has. They're supposed to be exactly the same. Either scavenged or somebody tried to repair it and gave up. If you look at the schematics, what I'm missing are the two Q1 and Q8, and they are the input transistors of the first differential amplifier, so they are the sensitive things, probably the first thing that you'd blow if you put too much of a signal over here. So interestingly, the transistor in question is from Fairchild, and that's the catalog that I recently scanned with my XUR scanner. So I have more info than what was on the web. Now it's on the web too. And it's a little bit of a race transistor which trades voltage capability is very low, 12 volts, for speed and noise figures. Supposed to work at around 1 milliamp, and with a noise figure of, it says here something like 4 dB at 60 megahertz, and it doesn't say how fast it actually is. And believe it or not, it's still made today. It's PN3563, which must be a much improved version of it. There you go. You see FT 600 megahertz. The one I have in my collection, I have two. One is a proprietary HP, which would be 800 megahertz, 20 volts. And then there's this one, which is a 2N5179, which is also 12 volts, very, very fast. Maybe too fast, actually, may have too much gain at high frequency and go into oscillation. This is why this has 4 leads, right? It has a lead for the case, so you ground it so it doesn't oscillate. So I might go for the slightly slower one, so I don't run into oscillation problems because the transistor is just too good. So I've put my 2 RF transistors to replace the original ones that were not as fancy. We don't know if there's more damage in the amplifier or if it has just been salvaged for transistors. Oh! I have the light, it's triggering. I have the marker, but my scope is getting tired. If I can get the scope to show a little bit better than that. Okay, banged the scope a few times and the bad contact came back, so I can see the marker. Yeah, with A and B. Excellent. More sensitive. That's right. And then we go to A to B. And now we need those to be on the middle. There we go. It's compensated perfectly. Okay. Hey, right. There we have 2 channels that work now. Very excellent. Okay, so next test is accuracy, and we run it off the clock of this one because we just adjusted it with the cesium, so it should be very close. And we generate 1 megahertz. We measure it down here with a 10-second setting. 10:00:32. So I'm a little off. The problem with the adjustment is going to take forever if I have to wait 10 seconds for each measurement. Let's put it in 1 second. And now we go to 10 seconds. Oh, not bad. I am 1 hertz off. There we go. Reads 1 megahertz. Okay, for the next measurements we have to temporarily steal this one from the Apollo setup because this little guy with this Nixie tube, it has an input at the back that can go up to 550 megahertz, half of a gigahertz. So this is this board. The way they do it is with ECL, which is 10 times faster than TTL, and it was an option for this machine. Unfortunately, I have it. I need to make a few pre-adjustments of voltages on that card. You have to go in the bowels of the card here and adjust the voltage to 0 volt, and it's 0.3, so that's not too bad. Okay, 0.000 something. And now that's when we turn to our microwave generator. Put it on the secret input at the back. 550 megahertz. Ta-da! 550. 540, 530, 520, 510, 500, 490, 480, 470, 460, 480 hertz, 440, 130, 450, 100, 1 400, 290, 380, 270, 260, 240, 330, we're going down, 180, 100, 10, 100, 10 hertz. 50 megahertz. Okay. I wonder how far it goes. Can we do 600 megahertz? You bet. Still doing it. It's not Chinese specs. It does the spec and then some more. 10, 20, 30, 40, 50, 60, 70. Yeah. That was it. 670 megahertz. Not bad for one that's specified at 550. Okay, we're not quite done because this is also a multimeter. So I brought the precision power supply, adjusted for 10 volts, tweak it. We want to go to DVM. Boop, boop, boop. And then we go to 10 volts. And it is unhappy and completely off. Does absolutely nothing. Alright, so we have another fault. This uses a voltage to frequency converter. So it actually does a frequency measurement which relates to the voltage. But it's not working at all. Fortunately, I have an extender that kind of works, so it makes it easier. I'm testing it on the bench. And I am testing the input amplifier and I'm the output of this. This should be a ×1 thingy. They made a JFET op amp with not having ones and old LM301. They just put JFET at the front, and that's the voltage I get at the output. It's minus 14 volts. So either that guy is dead or any of the transistors here is suspicious. I can hear the relays clicking, so that's fine. Okay, so I tested the current source transistor in the transistor tester, desoldered them, tested them, they were fine. So then I think, why don't I remove the feedback? And so I removed the LM301 over here and see if I get to measure something closer to 0. So I'll hook myself up to the output of the amplifier, which should be floating now. And you know, this is what I'm reading at the output of the amplifier. 9.99 going down, and now it's 9.99 going down. So I think it's working. It's just that LM301. Let's see if I can replace it with an LM301 or something better. So I don't have any old LM301s in my collection, but I have HP branded 741s. Okay, amplifier with a new brand can 741 instead of a 301. A better amplifier. See if it gets us back into business. It does not. Alright, so this is Q10, a lowly 3906 PNP, and it doesn't look like it's a transistor anymore. It's a short circuit. So maybe I found an extra bad part in there. And this is called a bootstrap drain supply. So I have no idea what it does. Some kind of analog wizardry. See if that made it. Ooh, 0 volts now. 1 volt. That doesn't work. Huh. Phew, I think we got it. So the original op amp was indeed dead. But what I replaced it with was not a single 741, it was a dual 741 with a completely different pinout. We put the real 741, and then all of a sudden, after a day of misery, things start to work. If I do 1 volt I get 10005. So let me read on how to do the calibration and we'll continue in a second. Okay, so apparently the drill is to turn this to 10 volts and do a fine adjust to 10.0000, and here's 10.32, and there's an adjustment on the frequency converter, and I should bring that to 10.0000. Now it's fully repaired. 10 megahertz, 9 megahertz, 8 megahertz, and if I put it back to 10, I repair channel B2, so I can do A to B average, and it gives me the 100 nanosecond it should be. It's also a DVM. That wasn't working either, but that's repaired. So look at that, 6 volts, 5, 4, 8. So that's a much better instrument than I thought it would be. And we are going to use it for our Apollo setup. Actually give it even one more functionality that it doesn't have. But I'm pretty happy with this. This was going to be scavenged for parts. Such a beautiful Nixie instrument. Wouldn't have that been a catastrophe. And now it's all good to go. All the tubes are working. Splendid.